thermo-elasticity. There is just one more thing that we have to do in order to finish thermo-elasticity. And then we'll talk about thermo-poro-elasticity, and then we'll talk about chemoplasticity and chemoelasticity. All right, so the last thing that we did was we used this constitutive equation in order to make run a few examples of what happens if you let a solid dilate, or what happens if you let a solid take temperature under constrained condition, and then last, what happens if you have a more realistic boundary condition, not fully realistic, but more realistic, that you have strain just in one direction. And we derive the equations that will tell us what is the change of stress with change of temperature due to variations of that's it. Changes of stresses due to changes of temperature. And this is a coefficient of proportionality. Okay, well, another very relevant boundary condition is the one in which you have axisymmetric conditions. Like, for example, when we have a wellbore, and what we are interested in this case is to get to know what would be the variation of hoop stress due to a change of temperature. And the answer to that, it's an equation which is very similar to the one that we just derived. It's very similar conditions, and this is just going to be the coefficient of dilation times the Young modulus. Actually, it's the same, divided 1 minus the Poisson ratio. This would be the stress, the change of stress that you would get here. In the tangential direction. And this one is actually at steady state conditions. That means that it's not changing with time anymore. So, for example, if you were to change the temperature 10 degrees, then your changing hoop stress would be this times 10 degrees. And when you now assume this, or when you add these changes of stresses due to change of temperature, the wellbore equations for hoop stress are going to be updated. And for example, at the point in which, let me add here a maximum and a minimum stress. Let's say this one is sigma 1 and this one is sigma 2, with sigma 1 larger than sigma 2. At a position like this one, you're going to have that change. And at a position here, you're going to have this hoop stress. The question is, where do you have the highest tensile hoop stress? In the top and bottom, or on the sides? Left and right. This is the maximum stress. So compressive stresses travel in this direction, and you're going to have tensile fractures that would initiate over there. And the equation at that place is going to be sigma theta theta. Let's call it location number 1. Location number 1. This is just a Kirsch equation at the, let me add that, at r equal to a. It's going to be equal to the pressure in the wellbore minus the pore pressure minus sigma 1 plus 3 times sigma 2 plus the change in hoop stress due to thermal conditions. So this one over there. And at the location 2, where you have more compression, you still have the same change, but it's not going to be that important at that point. Again, let me write again what this is in terms now of a delta. The change of hoop stress due to a change of temperature at steady state condition is going to be proportional to the coefficient of dilation, the Young modulus, 1 minus Poisson ratio times whatever change of temperature you have. Notice that since sigma 1 is larger than sigma 2, the equation is telling you that at this point is where you have the lowest hoop stress. This part is just Kirsch and it's just mechanical. This part is the thermal component. And when you have negative changes of temperature, then you're going to have negative changes of hoop stress, which mean more tension. If you remember what hoop stress looks as a function of the angle theta, it's like a sinusoid. And in this particular case, when theta is equal to 0, where this is theta, then we have the lowest stress, hoop stress. So this will be something like this. If you have a change of temperature, then this sinusoid is going to move. Let's say that we have a negative change of temperature. All the hoop stress is going to move. And the points in which you have high compression will have less compression. Points where you had some tension, you have more tension. And this is very important for wellbores because, as we said before, sometimes you change the wellbore mud temperature, and that may trigger changes of stresses that then produce mechanical failure in the wellbore. You may have events of low circulation just by changing the temperature of the wellbore.
The y-axis
Yes, stress. In this case, sigma theta theta. And here this is pi over 2, pi, 3 pi over 2. This is pi over 2. No, this pi. 3 pi over 2 and 2 pi. Hoop stress will be the smallest here. This is this point and there. Okay, well, so far we have talked about steady state solutions, but actually a real problem is not going to be steady state, and it's going to be a transient problem. And in order to solve a general problem of thermo-elasticity, you need to consider that part. And this general problem is going to have now, instead of, if you want to solve it also as a function of time, instead of 3 equations, and you're going to need 4. And it was the same thing with poro-elasticity, but I forgot to write these equations. But if you remember the 3 equations that we always need for a mechanical problem, first one is going to be equilibrium. We need equilibrium in thermoelastic problems and poroelastic problems. Second one is going to be the kinematic equations. Third one, we have the constitutive equation. But now for a problem of thermoelasticity, we saw that we have to add this component that is taking into account changes of temperature and how changes of temperature induce stresses and strains. And last, in order to put all of these as function of time, we need to know what is the variation of temperature with time. And this is going to be the, we are not deriving this from scratch, but it's very similar to the case of poroelasticity. And it's just a diffusivity equation where now we have the diffusivity of temperature, and here the main parameters are thermal conductivity, density, heat capacity. All of this is what is called thermal diffusivity. And you could solve a problem of temperature as function of time just with this part. But now we're adding the mechanical part. And this mechanical part has this additional component that tells you the variations of volumetric strain as a function of time and how that can affect temperature too. And it's just an expanded diffusivity equation. This is beta. This K is the bulk modulus. This KT is thermal conductivity.
So it's K sub T.
Yes, K sub T. Here, yeah. Initial temperature.
Oh.
Initial temperature T0.
And change in temperature squared? Is that
this one?
Yeah.
This is the Laplacian. The Laplacian, it's an operator that is a second derivative with respect to space of the temperature.
One more time. Second derivative
of temperature with respect to space. This one is a Laplacian operator. It's just a bunch of derivatives. Okay, but let's try to concentrate on the physical part. This equation, without this, is just a diffusivity equation of temperature. We'll tell you how temperature changes in a medium as a function of time and as a function of the thermal diffusivity. And this part is telling you what will be the change of temperature due to a change in volumetric strain. When you deform a solid, it takes energy as a strain energy, but also takes energy in the form of heat. I should bring one example, but if you have a piece of metal and you bend it back and forth, eventually it's going to heat up and it might break. And this is that component over here. A change in volumetric strain can lead to a change in temperature. Fortunately, in geomechanics, this term is relatively small. For typical parameters, all these things, and with initial temperatures which are like near ambient conditions, all of this about 50 Kelvin. And I could tell you for this example I used bulk modulus of 10 gigapascals, typical dilation coefficient, initial temperature of 300 Kelvin, typical density, and a typical heat capacity coefficient. But you will get something in the order of this, which tells you that, for example, if you have a typical change, which is already quite large, of volumetric strain of, let's say, 1%, then what you're going to get is, if you have a change of 1%, you're going to have a change of 0.5 Kelvin, which is quite small. So it's not like, for example, in poroelasticity that we could have, if we have a change of strain of 1%, that would give us a very high pressure in undrained conditions. In this case, you can have huge strains, and 1% is quite large, and still have a very mild change of temperature. So sometimes you can neglect this term. Or sometimes you can do a coupling which is not fully coupled, just solve the heat part and then solve the mechanical part without taking it into account this term. And again, if you had something even more realistic, like 1,000th of a strain, this would be 0.05 Kelvin, which is nothing. Imagine that you are modeling changes of temperature in the order of 100 degrees. It's nothing. 0.05 is nothing compared to 100. You have a question, Jack?
Yeah, the unit of 0.01
is a strain.
It's 1 over time, right?
Yes.
And for time, what's...
But the time is already here. So I'm just looking at that. The change of temperature that you will get as a change of volume.
Okay.
So if you have this given change of volumetric strain, you will have this change of temperature
So do you
in, let's say, 1 second or 10 seconds, whatever.
So in the geomechanical modeling world, do they actually use this equation to find the changing temperature of the surface?
In geomechanics, not that much. But if you were to model some other processes with high change of strain and temperatures, yes, you will have to account for that. All right. Let me. Yeah, I think, well, I have my other notes. Yeah, tell me.
How, how do you incorporate the seal of your reservoir or other properties? Because subsurface is huge, and here you have 0.01 like percentage of the string. So do you consider
No, this is 1%.
1%?
This is 1%.
Like 1% of a huge reservoir is still very huge, right?
It is.
So normally that string would be pretty small.
Will be smaller. Yeah, will be in terms of thousands. And sometimes you can get to high strains. But well, 1% is quite large. So, as I was telling you before, we also derived that diffusivity equation for a poro-elastic problem. And let me find it here in my notes. All right. It is this equation, and notice how similar it is, but instead of solving for temperature, here you solve for pressure. But you have this diffusivity parameter, and you also have this coupling parameter of volumetric strain as a function of time. But it's basically same equation for a different physical phenomenon. So if you want to fully solve a problem of poro-elasticity, if you wanted to write your simulator of poro-elasticity and solve problems as a function of time, you will have to use this equation, equilibrium, kinematic, that will be somehow embedded in your solution, and the constitutive equation too. With all of those, of course, with the constitutive part for poro-elasticity, not here for thermal, you will be able to solve a problem of poro-elasticity. All right, but since we were talking about poro-elasticity, let's now put together thermal part and the poro-elastic part. Let's see where, I think this is the way this should be. So I don't remember those equations by heart, and you should not remember them either, but you should know that there is a formulation that puts all of these together, and this would be the equations of thermo-poro-elasticity. And if you want to know more about this, you can go to the book of QC, and that's going to be in chapter 4.3. And basically what you do in this case is we already have the equations of poro-elasticity. We add the thermal part, and in terms of our energy equation, we will have a new energy term, which is a term that tells you how much energy you can add to the porous solid by changing temperature. So that will go in terms of entropy or heat, simpler version of entropy, and the additional variable that we're going to have is going to be a change of temperature respect to the initial condition.
Can you get out of focus, please?
Yes, I can do that. And therefore, after you do all of that, your equations are going to look like this, with poro-elasticity and the thermal part. The mean stress for poro-elasticity, we knew that it looked like this. Now we're going to have an additional term for the mean stress, which is a term that we have already seen before, 3 times beta k, where k is the bulk modulus, times the difference of temperature. Shear stress. Do you think temperature is going to change shear stresses? We said that no, for an isotropic homogeneous material, changes of temperature are not going to change shear stress, therefore there is no additional term here. Will changes of temperature change porosity? Maybe yes or maybe no. Yes, it's going to change, right? Because you have dilation. And that dilation is going to change the size of the pores. So here we're going to have an additional term that depends on change of temperature, where this term beta phi or beta porosity is going to be the beta of the solid part times Biot coefficient minus initial porosity. So it's just a dilation coefficient, but it is somehow weighted by the solid part. So remember, alpha, it could be close to 1 minus initial porosity. That will tell you the contribution of the solid part to this coefficient beta. And last, we will have another equation, which is the equation of entropy. So remember, it's entropy, porosity or change of porosity, shear stress, tensor, and mean stress. All right, so the entropy is going to be the initial entropy plus whatever heat you add by volumetric strain. This is similar to this term that we were talking about before. You add volumetric strain and you're going to have additional energy in the system. And there is going to be a change associated with pressure too. And one last term that depends on the heat capacity of the solid. So you solve all of those together, and then you're going to be able to solve a problem of thermo-poro-elasticity, accounting for the porosity and the fluid pressure. It's not, a lot more difficult to what we did before. Just one more term. All right, let's see how are we doing with time. We have about 30 minutes. All right. Let's do a list here of things we have seen so far. Okay, so we have seen, first of all, elasticity, right? Then we talk about poro-elasticity. Then we talk about thermo-elasticity. And if you put these two together, you have thermo-poro-elasticity. All right, now we're going to see another phenomenon or another type of a variation of elasticity, very briefly, which is visco-elasticity. And if we have time, we'll get started talking about chemoelasticity. Rocks are very complex materials, and the rocks are whatever you get. We do not design rocks, and sometimes they are very complex. They are porous materials. Many of our applications involve large changes of temperature, because rocks are natural materials many times. They exhibit viscous or viscoelastic response. And inside the rocks, we have minerals that react differently with different pore fluids. So we are trying, to get to address several actions that can modify the strain and stress in rocks. So poroelasticity done, thermo-elasticity done. Let's go with viscoelasticity. Okay. Let me start on a new page because I don't want to be restricted by space. There are several models for modeling viscoelasticity with their corresponding equations. But I don't want to go into that because we will need several lectures in order to address that completely. I would just like that you remember the three most common manifestations of viscoelasticity. And then later, if you're interested in the topic, you can go into the literature and find more about it. But let me tell you in advance that now this is a very important problem, and there are many people working on viscoelasticity in order to better understand stresses in situ and also how stresses vary as a function of time due to some engineering application. We're just going to see a very shallow version of viscoelasticity, but again, this is something very important. All right. First of all, let's go through some examples. I wish I had an example that we could play with here, but I don't. And I should think about getting something. If you get any idea of what I could use, just please let me know. All right. The first example, let me organize it here. I'm going to put schematic diagram, response, and example. All right. Let's say that we get a rock with its ports, everything, and to this rock you apply stress, an effective stress, sigma. And you apply this in such a way, let me also divide this in 3. You apply this in such a way that first you increase your stress up to a point, and then you hold that stress constant. I'd like that you tell me what you would expect as a strain response. And I'm making this very general, but you could think about this as volumetric strain. So clearly, if this is an elastic material, if you compress it, it should contract, right? And the more you compress it, the more it's going to contract. The question is, what's going to happen after you stop and you hold that stress constant? What do you think? Will the strain remain constant at the same value that was the last point here? Why would it decrease? We are keeping the stress constant. And now think of this like as a real material. Any other suggestion? So most materials, I would say all materials, depends just in time, but all materials are going to tend to creep, which means that this strain is going to keep increasing. If you keep the stress constant, the strain is going to keep increasing and it's going to go into an asymptotic trend. And whatever you get after this is what is called creep or a creep strain. You keep stress constant, but then it keeps deforming. And we just put here this creep strain. An example of this in petroleum engineering is the case in which sometimes you might drill through a salt formation, and if you don't case the hole very quickly, the wellbore may close on you as a function of time, because that salt was very happy with a given state of stress, but now you drill a wellbore, you change stress around the wellbore, salt doesn't like deviatoric stress, so it's going to tend to deform until it doesn't have any deviatoric stress anymore, and the wellbore is going to close. We don't have Rodrigo here, but Rodrigo could tell us some examples of this problem, for example, in Brazil. In Brazil, sometimes they have some rocks that tend to creep a lot, and as you drill them, the wellbore, after you pass the drill bit, they start to close. So if you don't case them quickly, then you're going to lose your hole. And that's what's called a creep strain. Constant stress, then you get a creep strain. All right. Let's see now the second case in which we're going to do the opposite. We are going to, let's say that this was the initial shape, and we compress it, and then we keep that strain constant. So what we did in this case was to fix some strain, and then we kept it constant. What do you think will happen with stress? Well, clearly, when we change the strain, the rock is going to react, and stress is going to change too. But what's going to happen after? It's the same rock, which is it develops or exhibits a viscoelastic behavior. So what do you think is going to happen with stress? There are three options. It increases, stays constant, or it decreases. Let me draw here the horizontal version. Why would it decrease?
Because it's able to flow, and it wants to get away from having this mark. Yeah, that explains it well.
So probably this particular example is not the best one to explain this, but you could also think this problem as if you had stress just in one direction. So if you compress it and then you keep it constant, the material slowly is going to tend to flow on this direction, or slightly it may grow some small cracks or grow some small cracks in order to relax that stress. Materials don't like to be stressed. Somehow they are going to relax that stress with time. And because of that, the stress is going to decrease, and it's going to tend it also with an asymptotic behavior. And this phenomenon is called stress relaxation. And again, this is because materials don't like to be stressed. An example of this is the variation in stress that you could have in a sedimentary basin as a function of time. So let's say that, let's see if I get this plot okay. It's kind of small, but I'll try anyways. Let's say that you drill, or you are trying to measure stress in a formation. And you know, not all rocks, but well, no, all rocks are viscoelastic. Some of them are more or less viscoelastic. The salt is just going to be one of the most sensitive rocks to viscoelasticity. But let's say that, you know, with time, you manage to get here, you have an extensional regime, and you manage to get a normal fault. A normal fault if this is the vertical stress, and somewhere here we have the pore pressure, a normal fault means that effective horizontal stress is low enough to cause shear failure with respect to the effective vertical stress. So we haven't got into that yet, but this is a shear failure, and this happens because sigma v divided sigma h is higher than the friction capacity of the material that we'll see later on, that we'll call that the parameter Q, or also depends on the friction angle as 1 plus the friction angle divided 1 minus the sine of the friction. And for it, put here 30 degrees, and you will get that this is about 3, for a friction angle equal to 30 degrees. So when the vertical effective stress is 3 times larger than the effective horizontal stress, you're going to get a normal fault. And what that means is, for this particular case, the total horizontal stress is going to be somewhere over here at the point in which the fault forms. Let me add a little bit of color to this. But this is going to be when the fault forms. Since salt is not going to like this extensional regime, and it's not going to like this stress anisotropy. At the depth of the fault, slowly this SH is going to tend to go into SB. And your SH is going to start to, in this case, increase and approach the value of SV. It might seem a little bit that I'm contradicting myself telling that stress is decreasing, but what you should think is that the stress difference or deviatoric stress is decreasing. Salt doesn't like the deviatoric stress, and that's what is decreasing with, that is what it is decreasing with time. So let me write that just to be clear. Deviatoric stress decreasing with time. And there are recent studies that say that a similar thing happens with shales. And the shales that have quite a large viscoelastic response, they also tend to flow with time so that the horizontal stress gets closer to the vertical stress. Just because shales and in general mud rocks, especially if they are soft mud rocks, they don't like deviatoric stresses either. So if you put a stress, they will tend to flow and to accommodate those stresses so there is no deviatoric stress. Okay. That's one example of stress relaxation. And I think I have some real examples in my set of notes about this. And let's see the third one. The third one is going to be, and let's do this one for a typical test of Young modulus in which we apply stress on a rock and this rock deforms. But the variable that we're going to add now is time, and especially what is called strain rate, which means how fast you change strains. All right, so for this particular example, if you were to measure, for example, the Young modulus, which is the change of axial stress divided the change in axial strain, keeping the other stresses or the confinement constant, then you will find that if you do one test at a given velocity, this one is going to be E, and what do you think is going to happen? Which test is going to have a higher Young modulus? One which is performed very quickly, or another one which is performed slowly? Which one is highest?
What's the question?
You're doing two tests. You're changing the same amount of strain. Let's say you take the two rocks to 1% strain. But you do one in 1 second and you do another one in 1 day. Which one is going to have the higher Young modulus? The one with in 1 second or the one in 1 day? Which one? Why the fast one? It's all linked, and you can actually, when you put some numbers into it, you will see that everything is linked. this is a function of time. Look how creep strains, stress relaxation is a function of time. And because of that, this is also going to be a function of time. And if you do a test which is slow and you do another one which is fast, the one that's done at the fast velocity, that's going to have a higher Young modulus. And there are several reasons for that. Some of them are involved, for example, if you had a porous rock, you could go into undrained loading. So if you have undrained loading, you also are compressing the fluids, and that makes your rock stiffer. Another cause of that could be when you are compressing a rock, and if you do it very slowly, you have some cracks, and we're going to get to that later on, that do not propagate immediately, but they are a function of the state of stress, which means that if you have very high stresses, not yet at failure, but high enough, you may have small cracks that propagate slowly. So if you do a test very quickly, you're not going to have that time for those fractures to propagate, but if you do it slow enough, those fractures are going to propagate slowly, and eventually your material is going to be softer. And an example of this, when you have a high modulus and a small modulus, is when you subject rocks over a long time to deformation, and probably a rock which may be quite stiff, let's say a sandstone, when you deform it over a million of years, you can fold it like it were something like very deformable, but actually it is not. But if you do it slow enough, the rock looks like it is much softer, which means lower stiffness, and it can deform very easily. If you do that quickly, it might turn into a fault, and it might break. It might take enough stress that it just breaks very quickly. And I hope we'll get to see this later on, but this behavior is also linked to those of you that are working on natural fractures, to something called subcritical fracture propagation. When you have this subcritical fracture propagation, which means propagation at the stresses lower than the critical value, your rock may start to crack in time, even though it's not at the maximum stress. And eventually that may make the rock look softer. And one more example, it's also, for example, in granular material, when you have stresses and they are equilibrated, but slowly you may have some grains to slip with respect to each other with time. Very quickly, you may not have that slippage, but over time, particles reaccommodate, slip with respect to each other, and that also can yield a response in which the rock tends to be a lot slower or a lot softer than if you do it very quickly. Okay. This?
Yeah.
This would be just I would call it particle rearrangement. And let me add one more thing. Over time, also, some of these particles may break, and that also makes the rocks look softer. So this would be particle rearrangement plus crashing. In the case of the salts, for example, it's similar to this, but instead of having particle rearrangement, it's just you have the crystals of the salt sliding with respect to each other. That's what makes the salt flow. All right, so this is all what I want you to remember from viscoelasticity. The creep strain, stress relaxation, and the last one is the dependence of stiffness dependence on strain rate, or strain rate dependent stiffness. Let's write it down.
So
Yes,
the stiffness is dependent on the strain rate?
yes.
Okay.
Or
The strain rate is not dependent on the stiffness.
no, the stiffness depends on the strain rate.
Stiffness.
Yeah. And you know, sometimes this can be a real issue because we do experiments in the laboratory that usually are done in sometimes less than an hour. For sure, in many tests, less than 1 day. But we may want to apply some of those results, let's say, to compaction of a reservoir over 30 years. The YAM modules that we use and we get from the laboratory is going to be a lot higher than the actual YAM modules over 30 years. And so that incompatibility sometimes is a real problem because what we measure in the laboratory is not really what happens in nature. All right, guys. I have one more topic to talk about, but I think we're running out of time, and we are more or less okay with the schedule of all the topics. So I think it's okay if we finish here. All right? Okay. You're welcome. Yeah.